So today we discuss the results of the youth challenge. So we had the youth challenge this weekend, and here are the results. Actually, pretty good results. A lot of people solved a lot of problems. Probably last problem was a little bit too hard, but it's supposed to be too hard actually. So we was worried that you are too smart and you will solve everything in 2 hours. So we left the last problem to be. So it's still doable. I will explain you how to do it. It's not that hard. It's not impossibly hard. It's just hard. Yes. So we will discuss everything about the last problem as well. So let's start from the first problems. First problems are pretty easy. So in the first problem, what you need to do, you just need to do what stated in the problem statement. Actually, the fun story is that the problem statement is exactly what happened in this contest. So we after the testing phase, we discussed that problem set is too hard and we need another easy problem in the beginning. So that's how we add this problem to the problem set. Like not in the last night, yes, but like few days before the contest, we added this last problem because contest was too hard. And we thought a lot about the easy problem for the first position. And at some point, I just added this problem so that with the same legend as actually what happened in practice. So what we have in this problem, we have some problem set. We need to add one more problem. And you have just two conditions. You have condition that the difficulty of this problem must be not greater than difficulty of all existing problems. And the sum of difficulties should be not greater than m. And if you look at these two constraints, they just tell you what is the maximal possible difficulty of the new problem. So if you increase the difficulty of the new problem, at some point you will break both these conditions, then one then another. It's in some order. So what you just do, you need to look at these conditions. So what these conditions tells you? The first condition just tells you that this new problem. So if x is the problem difficulty of this new problem, x should be not greater than minimum of all ai, and also you need to say that sum of difficulties, so sum of all ai plus x should be not greater than m. It just tells you that x is not greater than m minus sum of all ai. Yeah. So you check this condition, you check this. You check this condition. That's it. Let's check this condition. And find the maximal x that satisfies the condition. So you just tell x, it will be just minimum of these two. So the minimum of minimums of ai and m minus sum of ai. Yeah. So that's your final answer. Easy problem for the first position. So some of you solved it in just 3 minutes. Okay, maybe even less. Good. So that's kind of problem. Oh, some even 1 minute. Okay, that's perfect result actually. It's actually impressive to solve it in 1 minute. So you need to read the problem statement, understand what's going on. So it's impressive to do it in 1 minute. You're very fast. But if you not do it in 1 minute, if you do it in 10 minutes, it's still fine. Yeah. So it's just the first problem, just to you just get some speed. Yeah. Just first problem to start the contest. So I believe almost everybody solved the first problem. Yeah. Actually, a lot of people solved a lot of problems. Very impressed. So more than 200 people solved the first problem. Nice. In the second problem, we have, it's complicated solution. So it's complicated problem statement. So we have n identical dice, and we know that faces with numbers 1 and I and m minus plus 1 minus I are on the opposite side of this dice. So every dice has some faces. On each face there is a number from 1 to m. And we know that these two faces are on the opposite side of the dice. It's actually like the normal dice. If you look at the normal 6-faced dice, like cube, yeah, it has 6 sides, and sides with numbers 1 and 5, 2 and 1 and 5, 1 and 6. 1 and 6, 2 and 5, 3 and 4, they on opposite sides of the dice. And it's something similar happens here. So I don't know what is the geometry of this dice, but it has some m sides with these numbers on the opposite side. And what you need to do, the following thing. You throw all the dice, and then you just turn at most k dice on the opposite side. So if you have small number on the dice, you can turn to the opposite side, so it will move from number I to number m plus 1 minus I. Then you calculate the score as just the sum of all numbers of all dice. And the question is to find the minimum possible value you can guarantee, maximal you can guarantee. Yeah? Okay, it's a complicated statement. So what we need to do? So imagine you kind of want to find the worst possible situation. So you throw the dice. You have some numbers on these dice. Then you can turn over some at most k dice, and then you calculate the result. And over all these situations, you want to find the worst one. Yeah. And you need to output this worst one. So in the worst, what can you guarantee in the worst possible case? If you have worst possible throw of all dice, what sum you can actually guarantee? Not very intuitive problem. So again, if you have a good intuition, what you may have, especially if you read these examples and hear explanation of these examples, yeah, and you kind of think, what is the worst possible situation? What can be the worst possible result of throws of these dice? And you may think about two problems. So first, let's see. Yeah, like in this second case. In this case, I have dice with 4 sides. Yeah, and I can guarantee at least 3 on each dice. So the worst possible case, actually, when I have, if you have number 2 or so 3, you have like 2, 2, 2, and 2. Yeah, I can transform into 3, 3, 3, and 3. Yeah, so it's like one possible case. So again, these two chosen is because I have 1, 2, 3, and 4. I can transform 2 to 3 and 1 to 4. Yeah. So if I have 1, I will always transform it to 4. So in worst case, I may have 2 or 3, doesn't matter. Yeah. So if I have 2 or 3, I can transform it only to 3. Yeah. So it's the maximal value I can guarantee. Good. So that's one case. So if I have number like this, I can guarantee something like this. You can kind of generalize this case. So if I have, let's say, you have multiple, so you have. That's m over 2. So if I have m, then this value is actually m over 2. Yeah, m over 2. And again, let's say m equals 4. If you have not 4 dice, if k is not equal to n, if k is small, then what you can do? So you have some numbers of 2s, then you can turn over k of them. Yeah, so we'll have something like 3, 3, 3, 3, and then 2, 2, 2. That's one kind of bad case. What can you throw in the result of your dice? Another bad case is when you throw your dice and you have a lot of 1s, especially if k is small. So if k is small, so imagine your k is very small. So you have a lot of 1s. You can turn only some small number of these dice. Yeah. So you will transform them to k's or to m's. No, I mean 4 in my case, yes. M equals 4, I transform to 4, but all other will stay 1s. Yeah, that's also like, it looks like a bad case when k is small. So when k is large, this looks like a bad case. When k is small, this looks like a worst case. Okay, it's just intuition. Yes. So again, if you play a little bit with this game, you may see that one of these cases looks like a worst case for this game. It turns out it's actually true. So one of these cases is actually the worst case. So always one of these cases is the worst case. So you have two possible worst cases. You have worst case when all numbers equal to m over 2. m over 2. And you have bad case when all numbers equal to 1. So one of these cases will always be the worst possible case. So you transform the first one. Let's see. You transform the first one to, so you turn over k of the values. So you say m over 2 plus 1 k times plus everything else n minus k times. Yeah. And in this case you turn k values. So you have m of my k plus 1 multiplied by n minus k. So one of these one of these values is actually the worst possible values you can get. And you just calculate minimum of these two, and this is the result. If you want to prove this, not like I just show you like by intuitive some thoughts. If you want to prove it actually mathematically, you can do it like this. So imagine you throw some dice. So what will happen? So you have some increasing values of your dice. Yeah? Let's make a new slide actually. So imagine you have some increasing values of your dice. Yeah. Then when you turn over some dice, you will turn over some minimal dice. So you turn over these smallest numbers and you turn them to n minus n. So you turn them like this. So you get these values. Yeah, instead. So instead of this, I get these values. Now you can see that all the values here can be decreased to this value. It will be only better. Yeah, and the same here. These values can be decreased to this value. Yeah, so all values here must be the same. All values here must be the same. If they're different, you can decrease something and get the worst result. Yeah, so you decrease the final result. And after that, again, you look at this number and see if these two positions are different, you can move this position down and this position up. And they meet at some point. So at some point, you will have the same value here and here. So that's how you, again, you just by making small changes, you can achieve the result when all numbers are the same. That's how you prove that all numbers must be the same in the worst case. And now when all numbers are the same, you just write this. So again, when you turn over the first k values, what result you get? You have m plus 1 minus let's say x. So value is value is the same, it's equal to x. So I turn over k first value, so we have m minus 1 minus x multiplied by k plus everything else x multiplied by n minus k. Yeah. So you just write that. So after you proved that all numbers must be the same, you just write the result you will get if all numbers equal to x. And then you see you have linear function. Yeah. So you have linear function. Linear function is easy to maximize. So I want to minimize. I want to minimize this linear function. Yeah. So linear function has minimum in one of the ends. So you have some range of possible x's and you have some linear function. So linear function have minimum in one of the ends of the segment. So this is why I have two options. Yeah. So this option is 1 and this option is again m over 2. Yeah. Because x should be less than m over 2. Yes. All numbers must be small here. If m is greater than m over 2, I will not turn over anything. Yes, I will just keep all numbers. So minimal value for x is 1 and maximal value is m over 2. So you have linear function. So minimum is one of these in one of the ends. This is one you have these two cases, and you just choose the minimum of them. Okay, it's not that easy problem. I agree. So again, if you have good intuition, the good thing that you have programming contest, not math contest. So you don't need to prove this. You can just implement this and submit it, get 100 points, and be happy. In math contest, they will ask you to prove this. Yeah, but if you have good intuition, you can just solve this problem in like 8 minutes. Yeah. So these people are the 4 minutes. So these people are the good intuition. Intuition is a good thing. You need to train it in programming competition. It actually helps a lot. It saves you a lot of time when you have problems like this. Good. Any questions? Any questions? No. I don't read the code because code should be easy. Let's read any of them actually. Boom. Let's check somebody's code. Okay, anybody. Oh yes. So what? Must do. Oh yes, that's it. So okay, so it's overall. So okay, this kind of strange code, but yes. So you have minimum of these two values. You can just okay. I don't know what the reasoning behind these formulas. I believe they also work. So it's minimum of some two values. So maybe have some different reasoning why you have these formulas. That's more like it. So that's my formula. Yes. So you have this and this. So you have m over 2 plus this minus k. Problem C, on other case, has, I believe. So again, it's kind of standard easy problem. If you didn't say anything like this, then it's time to learn it. So what we have some periodic structure. So we have initial configuration of lamps, and we just switch the state of lamps with some step. So we switch lamp 0, then lamp k, 2k, 3k, and so on. So we move with step equal to k. And we need to answer the question: what will happen after some number of steps? So you spend d seconds, yeah, and we need to say what will be the number of lamps turned on when you after d seconds of this process. Pretty standard problem. If you solved one of these problems before, you probably already know what will happen. If you didn't, then it's okay. It's every time you have for any type of problem, you have the first time you solve problem. So what you need to do? You need to think. Okay, I have some periodic process. Maybe the states are also periodic. So if you have some periodic process, sometimes, not always, sometimes you have some periodic structure of states. Yeah. Let me again. Let me write here. So imagine you have like, let's say you have 1, 2, 3, 4, 5, 6, 7 states. Yeah. So I start here and move with step, let's say 2. So I jump here, then I jump here, then I jump here, then I jump here, then I jump here, and here, and then here. Yeah. So I end up in the same state when I started. So I started from this position, make the full turn, and finish in the same position as I started. Yeah. After this, I will jump over the same sequence of lamps. What it tells you? It tells you that actually the sequence of lamps is kind of fixed. Yeah. Well, again, let's make like 1, 2, 3, 4, and it's from 0. Okay, from 0. Let's see. 0, 1, 2, 3, 4, 5, and 6. So I have sequence like 0, 2, 4, 6, then 1, 3, 5, then 0. Yeah. And then we'll continue the same. So this period is the same. And yes, you can just tell me by examining what's happening in this problem. Now, what about sequence of the lamps? So what will happen after I finish one period? I stay in the same lamp. So like in this case, it might be, sorry. In this case, I start from 0, end with 0. So I turn on some lamps, or switch states of some lamps. Yeah. So for some lamps, I actually switched their states. So situation here will not be the same as here. Yeah. But if I repeat this once again, you do all the same period to 5. Then I switched all these lamps twice. Yeah. So here I am actually standing in exactly the same state as in the beginning. So I switched some states of the lamps twice. So the state is the same as in the beginning of the process. So after 2 periods passed, I stay in the beginning. I stay at lamp 0, and the state of all lamps is the same as in the beginning. So this is the interesting period of my process. Now what you need to do is just if you have this number d, you have period of size, let's say p. Do we have p? No, we have p. So if you have period of size p, you just take this number d here, number d, and calculate it modulo p. Yeah, because you can discard any of size 2p. Yeah, so you take this number d, calculate it modulo 2p. Yeah, and it will be just so you can just skip every period of size 2p because it moves you to the same position as before. Yeah? And now I just need for every remainder modulo 2p, I calculate number of lamps turned on. For this, I just simulate one period. So you simulate one full period. For every step, you remember how many lamps are turned on now. It's easy because every time you switch state of one lamp, so you either decrease number of lamps by 1 or increase by 1. Yeah. So after you switch state of the lamp, you just remember what is the current number of lamps. If you turn it on, you increase number. If you turn it off, you decrease the number. Then you will calculate number of turn up for every position on this period. And that's all. Now you calculate this number modulo 2p, know in which position on the cycle you're on, and then for every position you pre-calculate, yes, the number of lamps for this position. So you just output this position. So how to find the period? You can just find the period like this. So you start from position 0, find the next time you go to position 0, this is length of the period. Actually, for this problem, it's easy to see that length of the period always is some divisor of n. It's actually greatest common divisor of n and k. So you can calculate like this. Or you can just ignore these periods as well. You can just make n steps. So if you start in position n, 0, and make n steps, you will go to position 0. Because after n steps, you go to position nk modulo n. So it will equal to 0. Yeah. So you can just simulate first 2 n steps. You just don't care about the length of this period. Yeah? So you can think that the length of the period is n. It also works. So that's all. That's basically the whole solution. So we find the length of the period, then calculate for each request its position inside this period, and then for each position in the period we pre-calculate the answer. Yeah. So we just calculate my d modulo 2p, find the answer for this position, and just output it. That's all then. So let's check someone's solution. Oh, that's nice. Question. So, okay, so that's what you do, yes. So you have array of size 2n. Because 2n is always a period. If you make 2n steps, you go to the same state as in the beginning. Yeah, so I just simulate, so not me, just you simulate. You simulate first 2n steps. Yeah, and remember the state, the answer for each step in this first 2n steps. Yes, I have array of size 2n, just yes, s is my current counter. Yes, it is. No, okay, possible. Okay, that's actually nice. I love this code style. So again, S is my total sum of all elements in X. So how do you recalculate the sum of all elements when you change one element? You first remove this element from the sum, then change the element, and then add it back. It's actually a very universal way to update the sum when you change something. Not only sum, so basically any function that you can update. So when you have some function of your elements, you remove one element, fix it, not necessarily change it. You remove one element, change it, and then put it back. Yeah, I love this code style actually. So that's how you normally do it. Yes, and then just move x. That's all. And here I just calculate x modulo to n. Yes, and output the result. Very clean code actually. Good. The problem is like this. It's not very math heavy problem. It's more implementation heavy problem. So it's coding problem. So what we have here, we have some tokens placed in some squares on the grid, and we need to place one more token. And when we place new token, we calculate score like this. We take this newly placed token, calculate the longest horizontal segment that token belongs to, and longest vertical segment that this token belongs to, and just sum of these two lengths will be your score. And what you need to do, you need to find the best move. So you need to find the position for the next token in such a way that the sum of these two lengths is maximal possible. Again, let me draw something like that. So I placed a new token here, so this is the new token. So you look at all previously placed tokens here and here, yeah, like this. So your score for the move will be sum of this length plus this length, and you want to maximize this pair. Now, again, multiple ways to solve this problem actually. No, first of all, if I want to place a new token, where I want it placed? No, it kind of make sense if there is at least one token, and there is at least one token here. Yeah. So it kind of makes sense to place new token next to some previously placed token. So if you just place new token in the middle of nothing, yeah, here, you will get 2 points. Yeah. But if you place new token just close to some another token, you will get at least 2 points. Yeah. So you always place new token in some square which is neighboring of some existing token. Yeah. So what we can do first, we can iterate over all existing token and find all the closest positions. So for each existing token, you look at all neighboring positions. Yeah. And check only this position. So these are only positions when it makes sense to place a new token. So you only place token in the neighboring square to one of the existing tokens. No, again, it is just simple implementation task. So you iterate over all positions, check for neighboring positions. For every position, you check if it is not occupied by token. So if it is free square, you add it to the set. Basically maintain a set of all interesting tokens or all interesting positions. Yeah. Now, how to check the score for position? No, if you want to place token in this position, you go to the left, find the number of tokens to the left, find the number of tokens to the right, number of tokens above, number of tokens below. Yeah. You can just do it using simple while loop. So you just move to the left until you find the first empty cell, and move to the right until you find the first empty cell. Then you know number of cells occupied by tokens in your segment. Yeah, and the same for the vertical segment. So just while loop to the above, so while loop below. Again, it's actually can be implemented really easily. So you just need to go in all 4 directions, find the number of tokens in these directions. You can do it all using simple while loop. It looks like this algorithm is complexity n square because I need to look at n positions. Yeah, so you have n positions. For every position, you need to look in all directions, and you may have up to n tokens in all directions. Yeah, so n positions, n tokens in all directions. Yeah, so I may have complexity like n square, but it's actually not. So if you look closely, how many times we count each token? So when I make this while loop, I count this token only if I move from one of these directions. So in one of the tokens. So imagine you have some situation. You have some tokens here. Let's put some tokens. Let's put some more tokens. So imagine how many times I count this token. I count this token when I try to put something here, when I try to put something here, here, or here. So every token can be counted only 4 times in these while loops. Yeah. So I count this token when I go from this side. So when I explore this position and I go to the right, or when I explore this position, go to the left, or this position go down, or this position go up. Yeah. So every token can be counted only 4 times actually. So total time complexity will be linear, despite the fact I have two loops. I have first loop iterating over all positions, and then second while loop iterating over all these consecutive positions. Yeah. Second loop will only count each token at most 4 times. This one, the total time complexity is still linear. Again, now we just need to implement it carefully. It may have some challenge. If you never implement anything like this, it may be challenging, but it's actually not that difficult. So let's check some of your solutions. I will not write my solutions today. So we have contest today is harder than we usually have in this coding club. So I will just read your solutions instead of mine. Let's check someone else. Oh yeah, something like this. Something like this. No, again, you call it DFS. It's not DFS. No, it's just while loop. You know. DFS is when you have multiple ways to go. If you go in one direction, you may call it DFS, but again, what we have. So here, I insert everything in S. Okay. Now for every position in my set, I go in 4 directions. Okay. No, okay, you do it in one step. Okay. So you go in both directions and just call this. overcomplicated. Okay, you do from the other end. Okay, so you do from the other end. So for every position, you go in this direction until you find the empty cell, and then you add to empty cell. Okay. Okay, so you go to this empty cell. Okay, you do it backwards. Okay, also possible. And here you check all possible positions. So you go in for each position, go in all directions. So find some candidate. If it is not occupied, then you calculate the result. Okay, why not? Plus 2 because you count your position twice. Okay, a little bit overcomplicated, but yet code is fine actually. Code is fine. Who was the first to solve this problem actually? I'm interested. 20 minutes. 11 minutes. Oh no, it's the wrong problem. Problem D. 20 minutes. Nice. Okay, this code doesn't look very pretty, but it's fine. Yeah. So that's what you need to do. Okay, I will simplify this part. I like what you're doing here. So instead of changing this code, you change the array v instead. Okay. You can also change the code. Why? I'm not sure why you're doing this. It's actually fine. I also sometimes do it like this. Sorry. So this I sorted in a certain direction. Now I reverse it and do the same in the opposite direction. Not sure why you care about directions here actually. I'm not sure why you care about the ordering of these elements. Since you have map. Because you copy this from this. Got it. So you need to go from right to left. So okay. Also a little bit overcomplication. So I iterate all elements from right to left, and for every element I say that the length of the sequence is this length plus 1. Yeah. So that's how I calculate the number of cells from this cell in this direction. Yeah. So for every token in every direction, I calculate number of tokens in this direction. Yeah, that also works. That's fine. It's just a little bit overcomplicated. But if you can do it in 10 minutes, I'm proud of you actually. Good for you. What we have in problem E? We had some array. And we calculated these two sums, sum of all elements to the left, sum of all elements to the right. Then I have these pairs of two sums, and we shuffle these pairs. So in the end, we have some shuffled set of pairs of numbers. And we need to restore the initial array from these pairs. It's not unique, so you can restore any array which produces this set of pairs. Okay, so what we have? So first of all, we have this simple subtask when all elements are non-negative. If all elements are non-negative, then you can look at this. For example, left sums will be in increasing order. So you can just sort all the left pairs, all the left sums, and restore almost all elements. Let me So for every element, you calculate sum of all elements to the left. So you have empty sets, one element, 2 elements, 3 elements, 4 elements, and 5 elements. So if you know all these sums, and you can get them just by sorting all elements L, then you can restore all elements except one. So this element will be difference of these two sums. This will be a difference of these two sums. This will be difference of these two sums. So I can restore all elements except the last one. Yeah. But to restore the last elements, you can do the same with values of R. So you can sort elements of R and restore the last element from right to left, and you only need one actually. So you can calculate two minimal values in array R, and difference will give you minimal element will be always 0. Yeah, so you have 0 and something. That something is the value of the last element. That's all. That's the whole problem. So you can get 30 points from this. Full problem is a little bit more complicated. So let's look at the full problem now. So what we have, first of all, let's try to restore everything that can be restored. So imagine, so you have elements. For each element, let's have some element. You know the sum of all elements to the left, sum of all elements to the right. So position I, let's see, sum of these elements, sum of these elements. So how can I find value of my element first? So it would be easy to find value of my elements if I have the total sum. So if I know sum of all elements, yeah, I would easily calculate my element. I will be just sum minus L minus R. Yeah? So I easily can calculate value of this element. Yeah? If I know the total sum. How can I get total sum? In terms, it's easy. So if you sum all values in this arrays, so if you sum all values Li plus sum all values Ri, you will calculate each element exactly n minus 1 times. Yeah? So for each element belong to one of these sums in all sums except one. It's all. Yeah. For all other sums contain this element. So if you calculate this sum, you will calculate each element n minus 1 times. So if you divide this by n minus 1, you get s. Yeah? So this is how you calculate value of s, and this is how you calculate values of all elements. Now that's something. We know values of all elements. We just need to find a good permutation. Yeah. So we just need to put these elements in order in such a way that we produce these values of L and R. Do we want to do it for this example? Probably not. Let's do it really quick. Like in this problem, I have 2 zeros, so total sum will be 2 plus 0 plus 1 plus 3 plus 0 plus 1 plus 4 plus 4 plus 5 plus 0 divided by 5 element by 4. Yeah. So it will be 2, 6, 7, 11, 15, 20 divided by 4. 5. No? And now you can get the values of all elements. So first element will be 5 minus 2, so it will be 3. Next element is 5 minus 1 minus 3, it will be 1. Next 5 minus 1 minus, so it will be 4. Then minus 4 minus 4, it's minus 3. Yeah. And then again minus 5, 0. So these are my elements. Now I just need to put them in correct order. How you do it? No, you may think like this. Let's try to put element in the first position. What element I can put in the first position? No, I can put element which has the left sum equal to 0. Yeah. So for the leftmost element, left sum must be equal to 0. Now, what happens if I have multiple elements with the same left sum? So I have multiple elements with sum equal to 0. So imagine you put some element with what element you put one of them, yeah? So imagine you pick one of elements and put it in the first position. Now, what element you can put in this position? No, you can put element such that, okay, so let's say L1 equals to 0, yeah? So this is the first element. I put element in position A1, yeah? So to the second position, I need to put element with L2 equals to A1. Yeah. And so it's value L to A2. Now to the third position, I need to put element where L equals to A1 plus A2. And the value is A3. Now you can think about it like this. So imagine you want to put some element. So each element performs like this. So when you put this element, so the sum here must be equal to, so imagine you have some element, yeah? So when you put it in your sequence, then before you put it, you have some sum. This sum of elements should be equal to Li. Okay? So before I put this element here, sum should be equal to Li. After I put this element, like including this element, sum should be equal Li plus Ai. Yeah. So every element is kind of transition from one prefix sum to another prefix sum. Yeah. So again, when I put the element, I have current prefix sum, and I move it from Li to Li plus Ai. Yeah. And now I just need to put these transitions in correct order. So every element is transition from one prefix sum to another prefix sum. Again, now if you solved problems like this before, you may have kind of flashbacks, because what's happening? I have some transitions from Li to Li plus Ai. And I want to put these transitions in correct order, so they can make chain of transitions. So I make chain of all transitions, yeah, and it's actually Euler-Tur in this graph. So you build the graph of these transitions. And what you need to do, you need to build the Euler-Tur starting from position 0. So first position must be 0. And now you just make this transition. So in this graph, you start from position 0, and then you make some transitions, building the Euler path in this graph. Something like this. Yeah. So you have this graph, and you just build the Euler-Tur in this graph. That's actually the easiest way to implement it. You just build this graph and use the standard algorithm to build the Euler-Tur. That's all. No, it's kind of maybe surprising that this problem turns out to be a graph problem. So when you see the problem, you think, okay, it should be kind of math problem or something like this. Maybe some greedy algorithm works, but it's actually a graph problem. It happens sometimes. Sometimes you have some structure, but when you explore the structure, you actually go to some graph problem, like here. That's all. Let's read one of your solutions actually. So, who was the first? Okay. A lot of people solved this problem. Really proud of you. So it's not easy problem at all. Who was the first? I don't know. These were you probably. Here we calculate edges like this. How you calculate edges in vector of pairs? Okay, why not? So I just make vector of all possible edges. Oh yeah, you just compress all coordinates, right? No, why not? You can compress all coordinates like this, or you can use maps. And here you call the standard algorithm. Okay, finding Euler-Tur is actually easy algorithm. So that's it. That's how you find the Euler-Tur in the graph. It's not hard. So if you never did it before, just learn how to do it. It's not hard algorithm. So you just call it. You build the graph. Call this. Call the algorithm, and you get your Euler-Tur. Yes, and you can just print the result. Nice. I did it differently, I believe. Is it my solution? Yes, it's mine. So I just use maps instead. So I don't normalize coordinates. I just use maps instead of vectors. So it's not array, just map. So I'm problem is I have vertices of my graph are possible values of the prefix sums. Yeah. So I'll just map from prefix sum to other prefix sums. Yeah. So I do not enumerate all vertices of my graph. I have this value of the prefix sum as the identifier of the vertex. Yeah. This is how I put this. And again, this is Euler-Tur. This is the whole program. So again, calculate the sum, calculate all values, build the graph, call diffs. Easy. Okay. Again, code is pretty easy because you just need to build the graph and then call the standard algorithm. But again, to find the solution is not easy in this problem. It's good, hard problem actually. So if you solved it, be proud of yourself. So what we have in problem F? We need to calculate number of ways to construct a palindrome. What can we do? So we have some prefix and some suffix. We can shuffle prefix, shuffle suffix, like here. So we have some prefix, some suffix. We shuffle elements here, and we get some palindrome at the end. And for every middle position, we need to calculate number of ways to construct a palindrome. Not very pleasant problem. So let's do it one by one. There are many difficulties in this problem. First of all, let's talk about palindromes. So how palindromes are constructed? You have some array. Yeah. How to check if you can construct? So if you can shuffle all elements. So if you have some array, have some array. How would you shuffle elements to make it a palindrome? There are two cases. When you have odd length, when you have even length. That's almost always happens when you have palindromes. You need to consider both these cases kind of separately. Sometimes you can do something general solution for both cases. Usually they slightly different, so you usually need to make sure you consider both cases, even n and odd n. If n is odd, then you just odd. Then you have array something like this. Let's see, 1, okay, 1, 2, 3, 3, 2, 1. Yeah. Then you just make pairs of equal elements, and you need that number of elements is even. So for each value, number of elements with this value is even. So let's say sin t of x is even. Yeah. So for each value, I have even number of these elements. When n is odd, it's almost the same, but you have one element in the middle. So you have like 1, 2, 3, 4, then you have 3, 2, 1. So you have all elements in pairs except one. So you have all counters even, but one counter is odd. Now, first, let's check if we can construct actually palindrome for this array A. So if it's possible to make a palindrome, then we can just fix this middle element. So we just know which element should be in the middle. Yeah, it is the only element which has an odd counter. Yep. Like, do we have example of this? Like here, 1, 2, 3, 2, 1. So if you look at this example, you know that 3 must be in the middle. So something may happen here, something may happen here, but this 3 is always in the middle. Yeah. So if you have odd value of n, you know which element should stand in the middle. Or you have just impossible, you need output sequence of zeros. Yeah. So if you cannot construct palindrome, then just all elements will be zeros in the input, like here. Yeah. Now, okay, we know which element stands in the middle for odd n. If n is even, we just don't care about middle element. We don't have middle element. We just have pairs of elements. Now, how we calculate number of ways to construct a palindrome? No, wait, let's look. So imagine you have array A again. Array A, and you split it here. Let's say we split it to the left from the middle. So left part is less than right part. Then how I construct palindrome? So what I do, I put some sequence here. Let's write it in. So I put some sequence of elements here. If I fix this sequence, I know which elements go here. Yeah? So I symmetrically put elements here. Now in the middle, I arrange them in some order. So I have this middle element. Okay? So I need to put something here and symmetrically put something here. So how I calculate total number of ways? I calculate number of possible permutations here. Then I take all elements here, subtract my elements from this. Yeah. Look at the remaining element, make pairs of them. Yeah. And for each, basically I need to find all possible permutations of these pairs. Yeah. So I have some elements A, B, C here. I find a way to put them here. It's not very beautiful. Sorry. So A, B, C here. I know how to put them. Say C, B, A here. Yeah. So again, the way I solve it is like this. I look at the smallest half. In this smallest half, I arrange elements in some order. Yep. So we need to calculate number of ways to arrange elements in this small half. Then I put here symmetrically the same permutation. Yeah. I need to check that this element is so I need to check that in the right part I have at least as many elements in the left part. Yeah. So I can make this symmetrical construction here. Now, I need to look at this difference. So let's do it. Okay, let's do it one by one. Now, I need to look at the difference here in the middle. So it's a difference between the right part and the left part. Yeah. So I took the right part and removed all elements from the left part here symmetrically. I get some remainder here. I need to take this remainder, make pairs of elements, and consider all permutations of these pairs. Let's see. So, for example, let's say I have how you do it. To do it, let's first look at this. Let's solve easy problem. So, how to calculate number of permutations here? No, normally, so if all elements are different, then number of permutations will be just n factorial. Yeah. If you have equal elements, then number of possible permutations not n factorial. It's just number of. So how you calculate it? The way you calculate it. Okay. Imagine you have some elements like say 1, 1, 1, then 2, 2, and 3. Yeah. 4. So imagine you have set like this. So how many ways to arrange the elements of this set? No, you calculate it like this. So you calculate number of all permutations, 1, 2, 3, 4, 5, 6, 7. Yeah. So number of ways will be 7 factorial. But some permutations you calculate multiple times. Like every permutation of these 3 elements will be calculated separately. But I don't care in which order goes these 3 elements. Yeah. So I need to divide this 7 factorial by number of permutations I calculate multiple times. So I divide it by 3 factorial. Yeah. Then I divide it by 2 factorial. And let's also divide, so for symmetry, divide by factorial 1 factorial. So this is how you calculate number of ordering of elements if you have equal elements in your set. Yeah. So you calculate n factorial and then divide it by number of each element factorial. So you basically you have counter number of elements for each value, and then you divide it by factorial of each counter. So again, so imagine you have counters. So you have C and T of x is number of elements equal x. Then what you need to calculate is total number of elements factorial divided by product of all. Okay, so this product just keep C and T of x factorial, something like this. Yeah. So that's the value you need to calculate. Yeah. Factorial of total number of elements divided by factorials of counters for each element. Okay, if you never saw this before, that's basically like binomial coefficient. In binomial coefficient, you have just 2 values. Yeah. So you have n factorial divided by k factorial and minus k factorial. Yeah. Here it's like division not in 2 groups but in many groups. Okay. So I have n elements. I kind of want to split them in these groups. So it's kind of similar to binomial coefficient, but generalization for not for 2 values, but for k values. Nice. Now, let's see. So what we have here. So we need to calculate this value for some prefix of my array A. So again, I have array A. For this prefix, I need to calculate this value. Now, when I increase the size of this prefix, I add one more element here. Yeah? I increase one of these counters. So I have new element x. Yeah? So one of these counters, C and T of x, will be increased. When I increase one of the counters, I need to change one of these factorials. But only one. Yeah? So again, you have this product. You need to remove one factorial from this product, change it, and then put it back. You can do it in constant time. You can divide by this factorial. Actually, you don't need to, but yes, it's more general way to do it again. You have product of some values. You exclude one of the values from this product, change it, and then put it back. So you divide by this value. You can divide because P is prime. So this model is prime, and it's okay. None of these values is divisor of it. So you can divide by this factorial, change it, and then multiply it back. So you will update the value of this factorial. So this is how we calculate these left sums. So these sums. This is how we calculate these sums. Now, what the sums in the middle? We need to do the same trick, but we need to calculate counters here. Counters here will just, again, we need to calculate the difference between the right part and left part. Yeah. So we calculate the same counters here, and look at the difference of these two counters. Again, when we move one element from right part to the left part, we update only one counter. Only counter for this element. And when I update this counter, we can recalculate all these sums in constant time. Yes? Because in this product, we only change one element. So we change this one element, update the product, and calculate the result. That's basically it. So it's in short, this is the full solution. If n is odd, you also need to make care that this middle element can be put in corresponding groups. So you need to make sure that this middle element belongs to the part which contains the middle. Okay, again, not very pleasant problem, but that's basically the full solution. So you move this again. You look at this border between two elements. Between two halves, yeah, and you move this border to the right. Every time you move the border, you move one element from one half to another. So when you move one element, you change one counter. When you change one counter, you can recalculate the value because you change only one element of the product. Yes. So you change this one element, recalculate the value, and just output it. Then again, move another element, recalculate it. Okay, and then you have positions to the left from the middle, to the right from the middle. You kind of need to calculate them separately, but you can calculate all the positions to the left from the middle, and then reverse the string, calculate all the positions to the right of the middle. And that's basically it. Now you just need to carefully implement this. Let's look who did it first. Okay, let's look at my high. Okay. That's just a template code for module operations. If you don't have something like this, nothing really interesting here actually. So we just have plus, minus, multiply, some standard operations. Here I believe here calculate power b, yes, by making binary exponential. Here you divide. You can divide by putting elements to power modulo minus 2 because modulo is prime. If you put elements to power modulo minus 2, you basically divide by this element. Yeah. So it's quite again. So this is just standard code for module operations. Here is standard code for factorials. Yes. I believe you just copied it from somewhere, but it's easy. You can just implement it from scratch. You calculate some factorials and you calculate inverse factorials. But because I need to divide by factorials, yes, if you remember this code, here we need to divide by factorials. Easiest way to do it is calculate inverse factorials. Okay, no, not very pleasant, but I'm sorry about this problem. Actually, if you spend too much time on it. But on the bright side, actually, if you implement something like this a couple of times, you get much better in problems like this. So nothing really intellectual happening on here. All operations are pretty standard. Yes, just question how fast you can actually solve all these small difficulties and get the full solution. I have map of frequencies. Why not? Why not? Yes, you also need to care if you have elements less than 0, it means the answer is just 0. So okay. So here you calculate number of elements less than 0. Okay, so that's okay. That's how do you? Okay, you divide by inverse factorial. Really? Why? Why? You can just multiply by factorial. You can calculate inverse factorials, then you divide by them. Not very clever way. You just can multiply by normal factorial. But still it works. Okay. Yes, here you multiply it back. So we remove value, change it, and then put it back. That's how we change the total sum. So you have total sum, total product here. Yeah. So I remove one element from the product. So I divide by this value, change it, and then multiply back. You can do it if values are not zeros. If values are zeros, you cannot do it like this. But if you don't have any zeros, that's fine. And then you just copy it twice. No, that's different. So how you take care of? Okay, I'm not sure how you take care of this problem with some elements. So borders to the left and borders to the right are considered different. Okay. No, I don't understand how to do it. Probably I missed something. So I think you need to carefully do it for the all borders to the left from the middle and to the right from the middle. But you just have the same code. No. Here you move into the middle, right? Okay, what tricky implementation? I'm not sure what's happening here. Yes. Okay, I got it. So yes, you just okay. Here you do it. Okay. Okay, so here you consider only positions to the left from the middle, and here you consider all the positions to the right from the middle. It's strange that this goes. So okay, you just inverse the order of the. Okay. Makes sense. Okay, so this part counts all answers for the left part. This part counts all answers for the left. Again, you can just reverse the whole string and repeat all the same parts. So if you know how to solve problem for all the positions to the left, you can just count positions to the left, then reverse the whole string, count positions again to the left, using the same code. Yeah, and then you have positions to the left and positions to the right. Maybe some tricks for you. Whew. Good, 2 problems left. Again, problem F was hard mathematical problem. It's kind of standard for people who know how to do it. So if you solve problems like this multiple times, you probably know all these tricks. If it's first time for you, it's really difficult. But if you try to solve combinatorial problems a couple of times, it should be better. Okay. Problem F. Problem F is a nice game problem. So game theory is kind of a huge topic. A lot of things happening. Here we have simple game of 2 players. When one player maximizes something, another player minimizes something. So first player wants to maximize total score, second player wants to minimize total score. That's all. So there are a couple of different approaches how you consider games like this. One of the approaches actually think about some symmetry in this game. No, first of all, let's look at this game. What's happening in this game? Before we analyze how we play this game, let's see what actually happening in this game. So we have some tree like this, and we put some values in this tree. And when we put some values in the end, we have some Boolean values in all this, so some bits. Yeah. Then we calculate paths for each leaf and calculate XOR of all these paths. Now, how the value in any individual node, how the final result depends on the values in any cell. So if you consider any one node, so it's some value x, yeah, how this value will contribute to the final result? Let's see. So this value x, it will be part of some nodes in this. So if I have some leaves in my subtree, okay? So every time I calculate value for my subtree, I will have some bit sequence with this bit x in the middle. So I have these 4 bits in the middle. Now, you immediately can see that if you have even number of leaves in your subtree, then this value will not change anything. So you can put any value in this position, final XOR of this axis will be still 0. Yeah? So if you have node which has even number of leaves in a subtree, then this value just will not contribute to the final result at all. So it doesn't matter who will put this value. Yeah? So you can put any value here, it will not change anything. Yeah? So first of all, there are places like this. So some nodes will not change the answer. Okay, let's just remember that you have some nodes. It doesn't mean that you don't need to make these moves. You can make this move, but it will not change anything. Yeah? In games it happens. Sometimes you need to change. You need to make move that doesn't change the final answer, but it just you kind of skip the move. Yeah. If you don't want to make the move, you just skip the move. Yeah. By making this non-important move. Now, if you have odd number of leaves, then you have odd number of bits. Then you will calculate XOR of all these bits, so this x will be in the final result. So now this x contributes to the final result in this position. Now imagine you have several nodes in the same position. So this node have 3 leaves, this have 1 leaf, and this also have 3 leaves. Yeah, and they all on the same depth in the tree. Yeah, so all these 3 leaves correspond to the final result in this position. So these 3 leaves or these 3 nodes, they all contribute to the same position in the final result. Yeah. Now, what does it mean? It means that whoever put the final value in these 3 nodes will finalize the result. So imagine you have 2 players and you have only these 3 nodes. Yeah. So you have these 3 nodes, they correspond to the same position. Well, first player moves, then the second player moves. If you are the last player who plays this bit, you can define the final value of this bit. Yeah. So for every depth in the tree, for every position in the final bit of this, only the player who put the last bit will define the value of this bit. Okay, this is the second observation. Yeah. So if you look at multiple positions on the same level in a tree, you only care about the last player who put the value. The last player who put value in one of these nodes will define the final value of this bit. Now we have problem like this. We have some position. So this is final result. Yeah. So this is result. It has some bits. Some bits are already defined. It doesn't matter. Yeah, some bits are not defined. Some bits are not defined, and we kind of challenge who will decide which bit. So some bits can be decided. Let's look at the following. So if the bit has an even number of nodes, so imagine to have even number of nodes on the same level. Yeah, then it's never optimal to place one of the bits. So imagine you have even number of bits. If it's your turn and you move one of the bits, the second player may use symmetrical strategy and put another bit, and then you have the same situation. You have even number of bits. Yeah. So if you have even number of bits, you make a move. Your opponent makes symmetrical move, and you have the same situation. You again have even number of bits. Yeah. So if you have even number of bits, your opponent make use symmetrical strategy. Good. Now, if you have odd number of bits, let's have 3 bits. Then we can make one move here. So we put one bit here. And now we leave the same situation. So now we have even bits. Again, if you have even number of nodes on the same level, you don't want to make these moves. Now, imagine, calculate number of interesting nodes on each level. So imagine you have like 4 nodes on this level, then 3 nodes on this level, then let's say 5 nodes on this level, then again 2 nodes on this level. Yeah. So for each level, I count number of interesting nodes. Nodes that contribute to the final answer. Now, how would you play? Again, I don't want to play here because it's even number of nodes. If I play here, my opponent will play here, and I have the same situation. Yeah. So I don't want to play here. So I will play in one of these, in one of the odd numbers. Yeah. So if I have odd number of nodes, I put one of these values. Then my opponent put one of these values. So we kind of do these steps one by one until we have situation when we have all levels contain even number of nodes. If I have even number of nodes on each level, then the second player will decide all these bits. First player can't do anything. Again, first player need to move one of the positions when you have even number of nodes. So I make any move, second player make the symmetrical move. So second player always has symmetrical move. So when you find out in position when all levels have even number of nodes, then second player will decide all the bits. Now, this is true for all groups of bits except groups of size 1. So if in some level you have only one bit, then the first player actually can decide something. So now the game works like this. First we challenge after this move. So we have, now we can, in one move, we can decide which bit will be here. So first player decide one bit, second player decide another bit, first player. So again, let's say, okay, first player moves here, then second player moves here, first player moves here. Yeah, so we kind of decide which bit will be in every position when we have only one bit. Now we have some odd bits, so we do them one by one. It doesn't matter in which order actually. So I do 1, I do 2. Now it's turn of the first player. Yeah. So this, for every turn of move of the first player, the second player has the symmetrical move. Yeah. So it doesn't matter what will happen next. All these bits will be defined by the second player. That's all. That's the whole solution. So again, what will happening? First we look at levels when we have only one interesting node. When we have only one interesting node, also we have some non-interesting nodes. We have some non-interesting nodes here. Yes. So we can also make moves in these non-interesting moves. Yeah. So we also, yeah. So now the game works like this. First, I have these levels when I have only one interesting node. When you have only one interesting node, you can just make this move and define the value of this bit. So we sort these levels from highest to lowest bits and define them greedily one by one. Now we have some extra moves. We have some extra moves when we have odd number of leaves in the level, odd number of nodes in the level, or when you have some non-important nodes. So all these non-important nodes plus these odd nodes in levels are some extra moves. So we make the extra move and see what is the parity of this number. So who will be the last? Now the last player will define all the extra bits. So all these remaining bits will define the second player. You can actually just look at the total number of empty nodes in the beginning, yeah, and you know who will have the last move. So the player that will have the last move will define all these bits. And like first player wants to maximize, second wants to minimize. So first player will make all these bits once. Second player will try to make all these bits equal to 0. Yeah. So you check what is the parity of this number. If it is even, then the second player has the last move. Yeah. So it will make all these bits equal to 1. If it is odd, then the first player will make the last move. So first player will make all these numbers equal to 1. Whew. No, that's basically it. That's the full solution. Difficult problem? Yes, difficult. But actually, actually, some people solve this problem. I'm very impressed. That's not easy problem at all. So it requires a lot of thinking and then actually some implementation also. So let's check some of your solutions. Who was the first? Hour 20, because you skipped this problem. Okay, let's check. So some people prefer this problem than problem about this combinatorics problem. Yeah, it actually makes sense. I would also prefer problem like this. Nice. What language is this? No idea. Okay, here I construct the graph. Assets. Equals 2. Positive level equals 2. I'm not sure. Okay, I believe here you check if number of leaves is odd, is even, then just increase this value. So this boss will contain number of non-interesting nodes, and if it is interesting, you calculate number of interesting nodes for each level. Okay, why not? Looks overcomplicated actually, but okay, I'm not sure which one does which in this code. Here you check. Okay, this is something I recognize. So here you check if you have only one interesting node. So and we count interesting nodes for each level. If I have only one interesting node, then I go from left to right. I check which. So I kind of alternate. I post 1 0 1 0. Yeah, I start with 1. Yeah, I put 0. I put 1. Then I put 0. Then I put 1. Yeah. And then I need to look at the final. What is boost? I'm not sure what's happening here. I'm not sure. Why I feel only 2? Why can it be more than 2? Because here, okay. Okay, so if it's more than 2, I make it 2. Okay, so you have, okay, that makes sense. That's only interesting case. So interesting case is when number of elements equal to 1 and when you have more than one element. Okay, so if it's more than one element, you just put 2 in this position. Okay, and here why? Okay. Okay, so you add all. Okay, basically you add all the positions except the last 2 is not important. So it's not important which one will take all the elements. It's another way to think. Okay, that's actually nice. That's another thinking about this one. I got your idea. So the idea is like this: if I have multiple positions here, yeah, basically you take them one by one, and it only matters who will take the last one. So who will take the last position will define this bit. So basically no one wants to take this position. When you take this bit, the next player will take this and will define this bit. So it doesn't matter who will make these moves. Yeah, it only matters who will make this move. Yeah. So I have this. All these bits are actually non-important. Okay. So you calculate total number of non-important bits, and then you leave only important bits, and then these all important bits will be defined by the second player. Okay, I got it. I finally got your idea. Okay, good. It's actually much easier than my explanation. So in the last problem, we need to find 4 positions in a tree with the same distance. So again, first thing you need to notice in this problem that how this structure looks like. So if you have 4 vertices in the tree with the same distance, it only can happen if they have this middle point. So actually you have this kind of center, and you have 4 points with the same distance from this center. That's the only way how you can get 4 points such that all distances are the same, because you have a tree. So now the problem is like this. Let's look at this center. So imagine you have this center, the same point X. Yeah. You need to, so if you, okay, how you solve this problem in n squared time, for example. You can look at this X, look at all subtrees. Let's say five subtrees. Not 4. I need to pick 4 of the subtrees and find the point on the same level. So I pick some level, and I pick points here like A, B, C, and D. Okay. Let's make it red. So you pick some level and and get 4 points on the same level. Now, how you can do it in n squared? You can calculate number of points for each level, and then kind of measure. So for each level you have this sequence. Yeah. So again, imagine you have this level. So you have number of vertices for each level for each subtree. So you have 5 subtrees. In first subtree you have 3 points. In this you have 1 point. Like you have 4 points. Then you have 2 points and 3 as well. Yeah. So for every subtree, number of nodes on this level. Yeah. So what you need to do is calculate sum of all possible choices to pick 4 subtrees and multiply these values. Yeah. So we calculate sum of all, C and, okay, let's see CNT. So CNT I of level multiplied by CNT J for level. Okay, let's call A, B, C, D. A, then B of the same level multiplied by C of the same level and multiplied by D on the same level. Yeah. So I choose 4 subtrees. For each subtree, calculate number of points on this level, multiply all these, yeah, and then sum for all possible choices of these 4 subtrees, and sum for all elements. Yeah? So this double sum is actually your result. Now, first of all, how you calculate this sum? So if you already calculated all these values, multiple ways to do it. So if you want to calculate, again, what you need to calculate? Let's reformulate problem like this. So you have array A. Yeah. Imagine you want to calculate sums of all possible choices of 4 elements. Yeah. So you want the sums of products of all 4s of elements. Yeah. The way you do it is calculate basically dynamic programming. You calculate D of, let's say, ij will be sum of all sets of, let's say, j elements on prefix of size I. Yeah. So you take first I elements of your array, let's say I minus 1, and take all possible sums of all possible products of j elements. So j is up to, so j is at most 4. And calculate all these sums. Calculate sum of all these products. And the way you calculate is very easy. So you have this number x, so, no, it's okay, ai. So you have last element ai, let's say x. So this is new element. You want to add new element to your prefix. So how you do it? So you calculate like this. So dij will be, so I take, so if this, so this sum contains of 2 parts. I have sets that don't use this x and sets that use this x. So sets that don't use this x are just di minus 1j. Yeah, so it's no x. And then plus sums that use this x. Sums use this x, the di minus 1 j minus 1 multiplied by x. So I take all possible sets of j minus 1 elements. Yeah? And I need to multiply each of these elements by x and calculate the sum. It is the same as take all this sum, multiply this sum by x. Yeah? So that's how you recalculate this sum. Yeah? And it can be done in linear time. So j is up to 4. So it's n multiplied by 4 values you need to calculate. Yeah? And you calculate each value in constant time, so you can do it in linear time. That's all. That's how you do it in n squared time. And it's enough to get 40 points. So if you're curious how to get these 40 points, it's like this. So you choose which node will be in the middle, then calculate for each level, calculate number of elements on this level for each subtree, and then combine them using this trick. And calculate sum of all products of 4 different elements. Whew. This already is kind of complicated task. So if you get these 40 points, good for you. And now how to get the total points? How to get these 60 points? We need to do kind of the same, but without choosing this. So again, if you look at this, you kind of notice that you calculate the same values multiple times. So we kind of calculate some subtrees multiple times. So we need to, when you see a problem like this, sometimes you can just do some strange dynamic programming over trees. But sometimes you can actually have centroid decomposition. It's what we have here. So we need to actually have centroid decomposition. First, let's solve easier problem. Imagine you only consider the rooted tree. So you have rooted tree, and you only consider so you have some node x. You only consider a case when all four nodes are below. So when you, for every center, all 4 vertices are below the center. Yeah. So you imagine you have some fixed node as a root, and you only count number of these 4 of nodes when all of them are below this x. Then what you can do something, I don't know what is correct term in English, when we merge small set to large set. So what I want to tell you. So I want to calculate. I want to calculate for each x. I want to calculate the array. So imagine you have like DFS. And for each x, I will calculate the array of elements will be counter for each level, like this. Not like this, like this. So for each level, I want to calculate number of nodes in this level for the node x. So for each node, I want to return array of counters for each level, how many nodes I have in this level. And you do this by merging small array to large array. So imagine you have node x, and it has multiple subtrees. And let's look at the, so you recursively call your function for each of these arrays. And each of these in each of these calls return you some arrays like this. Yeah. So you call, again, you want to calculate this array for node x. You call it node x, then you recursively call it for each child of this node x. And this recursive call returns you one of these arrays. Yeah. So for each child of the x, you know this array of counters. Now you need to merge these all arrays into big array. Yeah. So you do it like this. So if you just merge them like this and produce the new arrays in new array like this. So if you calculate sum of all this and put it here. Yeah. It's slow because you will create a new array of the same size in this array basically. You can create array of size n on every step. But if you look at here, so if you look at the maximal size of these arrays, this part will be the same here. Yeah. So you just need to transfer this part here. So instead, what easiest way to do this is actually merging small arrays to big arrays. So I will look at all these arrays, look at the biggest one, this one, and just merge all other arrays here. So you look at this array, you do just using very simple naively, just look at all elements and just add them to these positions. Okay? So you look at all these positions, just add them here. Just no intellect here, just iterator all positions and add them to these counters. Then iterator of these positions, add them here, iterator of this position, add them here. And then you get this array of sums of all these counters. Now what you need to do actually, you need to change all the levels. Because for all levels, you can add this x, so you have one more level here. So you need to increase all these levels by 1 and add this vertex s with level 0. And you take this array and just add one more. So you calculate. So again, you merge all these small arrays to the big array, and then add one more one to the left of this array. And this is your result. So instead of creating a new array, you take the biggest array, merge all other arrays to it, and then extend it to one position. And this is your final result. So you reuse the values from your biggest child. You take your biggest child and reuse its array in your array. Hope it makes sense. Again, this is quite standard technique, but it's not very easy to use. So you need to be careful when you implement something like this. It's not very easy technique. But after you learn it a couple of times, it's actually not that hard. Okay, this is how you calculate. If you know that all your values are below, this is how you do it. Unfortunately, this problem is even worse because I don't know if all positions are below. They may be above for me. So I may x. So I have let's say three nodes below and one node above something here. I say, yeah. So I have three nodes below x and one node above x. And this node is kind of tricky to consider. So I need to count number of nodes above x. It's very hard to do it in this concept. So in this concept, it's nice to count nodes below x. It's very hard to count nodes above x. So what I will do instead? I will do something that's called centroid decomposition. Okay, this is the final step. Okay, so what we'll do, you consider centroid of graph. Centroid is the point of the graph, this could see, such that the tree kind of breaks into part, and each size of the parts is no more than n over 2. So it's kind of like divide and conquer technique. So you find centroid, you solve the problem inside each of these parts, and then solve something in the middle. So first, let's solve problem in each of the parts. So in each of the parts, I will calculate just all these like stars of all possible four plets. Is it the word? So all possible choices of 4 nodes in each of the parts, I will just calculate recursively, like in divide and conquer. So I divide my tree in parts of size at most n over 2, and recursively calculate answer for each of these parts. Now I need to calculate answer in the middle. Answer in the middle means I need to calculate situations like this. Let's draw this part bigger. So something x here, then I have 3 nodes below x and 1 node somewhere here. Yeah. So I have 3 nodes below x and 1 node is below this. It may be centroid or something beyond this centroid. Yeah. Okay. And the way you do it is, again, you iterate on node x. Now for each level, you do the same. You calculate counters for each node x. You calculate counter of nodes for each level. Then for this level L, I know how many nodes I have in each subtree. And I also know, so I know this distance d. So I know this distance must be L minus d. Yeah. So above this centroid, I calculate the same counters of all nodes for each level. So I need to multiply counters for these nodes on level L from x and nodes and the count of nodes beyond the centroid on the length L minus d from the centroid. So before you do this dynamic, so you calculate these counters. So I will calculate these counters before. Then I will process this part of the tree. Yeah. So I do the same DFS that calculates counters for number of elements for each level. Yeah. But when I calculate final result, I kind of multiply all possible choices of 3 nodes on the same level, like before, and multiply it by number of nodes above the centroid on the same level, and add this product to the result. Oh. Hard problem. I agree. This problem is hard. Actually code is okay. If you implemented this couple of times, the code is not that hard. So I believe I implemented it in like half an hour. So it's okay. So okay. It's not. So let's read this solution. So it's not very hard. I promise. We'll read it very quick. So what do we have here? Here we have normal modular arithmetic because we calculate everything modular. Here, so this structure I use to calculate products. So I need to calculate sum of all products of every choice of 3 nodes. Yeah. So that's how I do it. I maintain 3 counters, sum of all single elements, sum of all pairs, sum product of all pairs, and sum of product of all triples. Yeah. And when I add new element to my set, I recalculate it like this. Yeah. Again, it is the same as we did, if you remember. So I should this is the same here. Yeah. I just simplify it because I have only 3 elements. Instead of making array, I just make 3 values. Yeah. So I use this structure to calculate sum of all triples of sum of products of all triples of elements. Now here, okay. Here, go. So this go is the center of function of all. So I give it some part of the tree and it calculates answer for this part of the tree. How I do it? I calculate size of this part. I find centroid of this part. Yeah, put x to this centroid. Now I look at all all the neighbors of center which are not dead yet. No, I don't remove these dead parts. I just mark them as dead. So here I look at all the neighbors of my centroid, basically. Here I calculate total counters, and then each time I process one of my neighbors, I subtract counters from these neighbors. So because if you look here, so here I want to consider counters for this part of the graph. Yeah. So I calculate total counters and then subtract counters of my part. So I have counters of everything except my part. That's what I'm doing here. So I have total counters, then subtract counters for my part. Then I call this function that calculates everything inside this tree and then put it back. So I subtracted them here, then add it back here. Yeah. So if you do it methodically, it's easy to read actually. So what we're doing here, so this function calculates, again, it calculates the array of counters and also calculate the result. Let's go here. Again, not very complicated. So what we're doing here, so we look at all children. Yeah, for each child, I calculate the result. So I recursively calculate the same function for every child. Because I want to reuse the same arrays, so this returns me index in arrays of array, in array of arrays. I have this array of arrays because I will reuse the same arrays. Hope it makes sense. So if I don't have any children, I just reuse empty array. If I have children, I find the maximal one here. So J is the index of the maximal child. And now I just add all other children to this array. Yeah? So I iterate through all children, skip the maximal one, and just trivially add all these elements from this. So I take this small array, iterate through all elements, and here I just add it to this array. I add it from right to left because it's actually, because I want to add 1, 0 to here. I need to add this one to that. So I'm doing it right to left. Okay. Hope it makes sense. So all arrays are reversed because it's easy to add to the end. I need to add this one. Yeah. Here, this one. I need to add 1 in the end. So I store all the arrays in reversed. Yeah. So again, I iterate over a small array, look at all elements, add them to big array, and recalculate the result here. Now this S is an array with triples. That's again. So these triples I use when I recalculate the answer. That's all. So now in the end I calculate sum of products of all triples for each level. Now I go over the sum of all triples, take this triple, multiply it by counter of elements above the centroid, and add this to the result. Then I take this merged array, add 1 to the end. I want to add it to the left, but it's reversed, so I push back 1. Yeah. And this is my new array. I just return it as a result. That's all. Here is actually some simple DFSs, couple of DFSs. So I have one DFS to calculate size, one DFS to find centroid, one DFS to calculate counters for each level. It's just some easy DFSs. This is the most, I believe this is the most intellectual part of this code. So here is just simple centroid basically. So this is here something intellectual happening basically. Okay, no, like you see, it's not that much code. It's a lot. It's much more than in all previous problems, and it is intellectual code actually, but it's not impossible. So I believe if you learn some more, you will be able to solve problems like this without much trouble. So very good results. I'm proud of all of you. Okay, so that's it. That's all problems. If you're not join the club, join the club. We have discussions of contests every week. So if you're interested, just join and we will discuss something else next week.